Picture this. The airplane you're boarding looks nothing like an airplane. No long metal tube. No skinny wings awkwardly bolted on. Just one smooth, futuristic shape that looks like it slid straight out of a sci-fi movie, and it might completely rewrite how humans fly. And here's the wild part. This isn't fantasy. This is engineering catching up to ideas we've been flirting with for decades. Tomorrow's airplanes are being redesigned from the ground up. And when they arrive, aviation as we know it won't survive the transition. For nearly 60 years, commercial airplanes have quietly evolved while pretending to stay the same. On the outside, it's been tube, wings, engines, wash, rinse, repeat. But under the skin, relentless innovation. Engineers have squeezed, shaved, optimized, and refined every possible inefficiency. And the results are insane. Here's one start that tells the whole story. Over the last 5 decades, the average amount of fuel burned per passenger per kilometer has been cut by almost half. Not because planes got smaller or slower, but because engineers refused to stop tweaking. Travel got cheaper. Flights got cleaner. Aviation quietly became one of the most efficiency-obsessed industries on Earth. Look at wings alone. Every modern airliner wears its efficiency like a signature. Split winglets, curved tips, fences, blended edges, each designed fighting the same invisible enemy, swirling vortices at the wingtip that act like tiny fuel-eating tornadoes. Those little add-ons you barely notice, they can cut fuel burn by up to 6%. 6% from a small piece of metal. Engines followed the same path. Bigger fans, higher bypass ratios, whisper-quiet thrust monsters that sip fuel compared to their ancestors. And yet, through all of this progress, one thing stubbornly refused to change: the shape. The tube and wing layout has ruled the skies since the late 1940s. The first time this configuration really took off, literally, was with Boeing's B-47 Stratjet. Long fuselage, swept wings, engines hanging underneath. For its time, it was revolutionary. For Boeing, it was a gold mine. That success funded the template that would become the modern jetliner. Then came the Boeing 707, and just like that, the tube and wing design crowned itself king of commercial aviation. And honestly, it deserved the throne. Circular fuselages are perfect pressure vessels. They handle repeated pressurization cycles beautifully, stretch the tube, shrink the tube, create variants without reinventing the plane. Airlines love it, regulators love it, pilots love it. It's safe, predictable, and scalable. But here's the uncomfortable truth. That same design might be the single biggest obstacle standing between us and the next massive leap in sustainable air travel. To understand why, we need to talk about balance, literally. On a typical airliner, the center of gravity sits forward, while the wings generate lift slightly behind it. That mismatch wants to pitch the plane nose down. To stop that, the horizontal tail pushes down. Yes, down. At cruising speed, that tail is actively fighting gravity in the wrong direction. That downward force accounts for roughly 5% of the aircraft's effective weight, which means the wings now have to work harder, generating more lift than they otherwise would. More lift means more induced drag. More drag means more fuel burned. And that's only half the problem. There's another villain called parasitic drag. Skin friction and form drag combined. Every square meter of surface touching the air adds resistance. Engineers call this the wetted area, and the tail alone can account for up to 35% of it on a conventional airliner. So the tail is doing two things at once, pushing the plane down and making it harder to move forward. That's not inefficient, that's tragic. Now imagine removing the tail entirely. That's the core promise of the blended wing body. No separate fuselage, no traditional tail, just one smooth, wide, lifting shape where the body itself produces lift. Suddenly, weight and lift are working together instead of fighting each other. The payoff is around 27% less fuel consumption. Let that sink in. If the world's commercial fleet magically switched to blended wing aircraft tomorrow, global fossil fuel use could drop by roughly 26 billion gallons per year. That number is so absurd it barely feels real. And airlines absolutely noticed. In an industry where manufacturers fight tooth and nail over single-digit efficiency gains, a 20+% reduction is a once-in-a-generation opportunity. That's why every major aerospace player, NASA, Boeing, Airbus, has spent years quietly pouring resources into this idea. In fact, one company bet everything on it. As competition from Airbus tightened and sales slowed, McDonnell Douglas made a desperate play. They began developing their own blended wing aircraft, hoping it would leapfrog the competition. That gamble didn't save the company, but the idea didn't die. When Boeing acquired McDonnell Douglas, the research lived on. Enter NASA's X-48. This wasn't a full-scale airplane meant to carry passengers. It was a flying laboratory. A way to answer one terrifying question: can a tailless passenger aircraft actually be safe? Because removing the tail removes more than drag, it removes passive stability. The tail isn't just there to look pretty, it's constantly correcting the aircraft without pilot input. When turbulence nudges the nose up, the tail automatically reduces downforce, letting gravity pull the nose back down. When the nose dips, the tail pushes harder, restoring balance. It's elegant, automatic, and brutally reliable. Take that away, and you're left balancing a broom on your finger. Early flying wings proved this the hard way. Humans simply couldn't react fast enough. It wasn't a matter of skill, it was physics. Eventually you lose. Everything changed with fly-by-wire. Suddenly, computers could make thousands of micro-adjustments per second. Aircraft like the B-2 Spirit became possible. If you've ever watched refueling footage of the B-2, you'll see control surfaces constantly twitching, working overtime to keep the aircraft stable. It works, but it comes with risk. Passive stability fails gracefully. Active stability fails catastrophically, and aviation learned that lesson painfully, more than once. The only B-2 ever lost wasn't shot down. It crashed because faulty airspeed sensors fed bad data to the flight computer. The system thought the aircraft was pitching down and commanded an aggressive nose-up correction at low speed. One wing stalled. The aircraft was lost. A $1.4 billion mistake. Then came the 737 MAX. Bigger engines forced a shift in engine placement. That changed the aircraft's natural stability. Instead of redesigning the airframe and recertifying the plane, software was added to mask the issue. MCAS relied on a single sensor. One failure triggered automatic nose-down commands. Twice. That wasn't just bad luck. That was a design philosophy failure. So if blended wing aircraft are going to carry hundreds of passengers, their control systems have to be perfect. Redundant sensors, bulletproof logic, zero shortcuts. That's exactly why the X-48 program mattered. Engineers weren't just flying models, they were harvesting data, testing control laws, teaching computers how to fly safely without a tail. And the results were promising. Now let's talk about the inside, because yes, it gets weird. Blended wing aircraft don't have traditional windows. The main cabin doors near the front might be the only place you see outside. For window seat lovers, that hurts. For claustrophobic passengers, it's concerning. Designers have proposed camera systems feeding live exterior views to seatback displays. Emirates already does something similar in first class. It works, but it doesn't quite hit the same as real sunlight. Other concepts, like the Flying V, try to stretch windows further back along the wing. It helps, but raises new challenges, especially during emergencies. Speaking of emergencies, here's a surprise. Evacuation might actually be faster. Instead of one long tube with 2 aisles, a blended wing can have 6 aisles with exits at both ends. Doors are closer, no 90-degree turns, no single person blocking everyone else while fighting their carry-on bag. Boarding and deboarding could be dramatically quicker, assuming airports adapt. And structurally, this is where the design really shines. Traditional aircraft concentrate weight in the fuselage and lift in the wings. That mismatch creates massive bending forces where wings meet the body. To survive, aircraft need heavy reinforcement. More weight, more fuel. A blended wing spreads weight and lift across the same area. The body itself contributes lift. Bending loads can drop by up to 50%. That means lighter structures, fewer reinforcements, and even more efficiency. It's close to the aerodynamic ideal, but there's one last monster hiding under the bed. Pressurization. Circular fuselages are perfect pressure vessels. Non-circular ones are not. Pressure wants to balloon flat surfaces outward, creating stress concentrations at joints and bulkheads. History has already shown us what happens when fatigue and stress concentrations meet. The de Havilland Comet paid that price with lives. So how do you solve it? Composites. Carbon-reinforced plastics change everything. The Boeing 787 already uses them to pressurize the cabin to a lower altitude, making flights more comfortable. Bigger windows, less fatigue, better durability. The same materials make blended wings possible. Designers proposed thick composite sandwich structures that act as both skin and pressure vessels. Fewer parts, fewer joints, fewer cracks. Some experimental aircraft have proven how radical this can be. One surveillance drone used just 3 parts for its entire fuselage. That's not futuristic, that's happening. Fewer parts mean cheaper manufacturing after initial tooling, fewer failure points, easier maintenance. And here's where everything connects. The future of aviation likely isn't just about shape, it's about fuel. Hydrogen has a volume problem. Tube and wing aircraft struggle to store it. Blended wings don't. Massive internal space, lower fuel burn, Suddenly, hydrogen becomes practical. That might be the final push. NASA engineers have already suggested we could see blended wing aircraft entering service within the next couple of decades. When they do, the change won't be subtle. Airports will adapt. Cabins will feel different. The sky itself will look unfamiliar. Before we go on, quick pause. If you're enjoying this breakdown, hit that like button, subscribe, and turn on notifications. It tells the algorithm you want more of this, and it genuinely helps the channel. Now back to the future. The technology is ready. The materials are mature. The efficiency gains are too big to ignore. What's left is trust. Aviation doesn't forgive mistakes. One failure can delay adoption for decades. But once the first blended wing proves itself, everything changes. And when you eventually board one, no tube, no wings, just one seamless flying body, you'll realize something quietly historic is happening. You're not just flying to another city, you're flying into a completely new era of aviation. If you want to keep exploring where engineering, science, and bold ideas collide, stick around. Subscribe. Share this with someone who still thinks planes peaked in the 90s. And I'll see you in the next one.